So in the last video you saw how to use Swift to set up a virtual wind tunnel and calculate the wind over a site from multiple wind angles and map those results back onto a single CFD mesh, giving you a cache set of results for multiple wind angles over a single site. So the next natural question is, what do we do with this information? Well, there's a whole lot of cool things we can do with this. We can calculate external facade pressures from multiple wind angles for structural loads. We can take the facade pressures and map those onto an energy plus airflow network. But in this case, what we're actually just going to do is show you how to use those results to actually calculate urban comfort over an area, specifically the wind comfort according to the Lawson criteria. So that you can see what the results look like, this map here shows the regions where the Lawson criteria is being met for certain activity types. So that's sitting in the dark blue, standing or loitering in the light blue, walking in the yellow, and exceeding walking in the red. It's not just the result for the whole year, it's actually 17 sets of results for 4 times of the day for the 4 seasons of the year, which gives 16 set of results, and a 17th result for the full year itself. So these, for example, this first time here is summer mornings from 7 a.m. till 10 a.m. And then we have summer midday, summer afternoons, and summer evenings. Then autumn mornings, midday, afternoons, evenings, and then winter, and so on, and spring. And the final result is for the full year. Now these results can be visualized in ParaView in full 3D obviously, but in this case we're just looking top down, so I'll remove the buildings and just look at the plane like this. On top of the comfort maps we can also get a map of the average wind velocity. Now it's important to realize here that this is not a vector result, these are average results for all the hours of the year, and this is showing velocity magnitude. It might look like you could put arrows onto this plot, but that wouldn't actually be correct because these are just averages of the velocity magnitude, so there is no real direction to these. However, this has been calculated using the Perth, West Australia weather file, and in Perth, Western Australia, in the summer mornings we have a strong land breeze effect. Generally the wind blows from the land out towards the sea, and in the afternoon, in the summertime, that is typically reversed, and the wind blows from the cooler ocean into the hot land. So in the mornings you get an easterly wind that would blow on this plot from right to left, and in the afternoons generally the wind will blow from left to right. And you can see that what's happening here is this average map is for the summer mornings is capturing the effect of the prevailing winds, and you can see that it kind of looks like the wind should be blowing from right to left here. This kind of looks like the right flow field for that. In the middle of the day then you get the winds transitioning from a land breeze to a sea breeze, so you get a bit of random everything, so it looks like the wind's going every which way. And in the afternoon you get a strong prevailing westerly, southwesterly wind, which you can see here the wind is very much looking like it has a pattern that flows from the left to the right. So what's really cool about this is that we're aggregating the CFD results across, well, either a full year or sections of a year, times of the year, and we're capturing the prevailing effects, which is really great. We can do all sorts of cool analyses with this. When you convert that back into a comfort map, you can actually see you get these prevailing effects. So in the summer mornings you can see that these areas might be exceeding criteria for walking. In the middle of the day you get going every which way, and in the afternoon you also get sort of a strong westerly prevailing pattern, and you get some wind tunneling and areas which are exceeding walking criteria here. So what's really great about this is we can get a lot of resolution, and we can break down a site and look at it for times of the year, times of day, seasonal effects, prevailing effects, and we can get really nice resolution on comfort conditions around a site. So how do we do this? You can go to the Swift website and download this tutorial by scrolling down to Wind Comfort Mapping Lawson Criteria and downloading the file. When you open it up in Grasshopper, it won't look exactly like this. I've actually taken these components here on the right and moved them off, and grouped these components on the left with a blue box. The reason I've put a blue box around these components is because we have covered all of this in the virtual wind tunnel tutorial which was covered in another video. So we're going to just go very quickly over this and gloss over a lot of the details. If you want more details, go back and look at the virtual wind tunnel tutorial video. And we're going to focus mostly on these components on the right hand side. So just so that you have an understanding of what the domain looks like, here it is in Rhino, and you can see it looks very similar to the virtual wind tunnel. The only thing we've done extra is we've added this ground plane here in green, and this is just a very thin box that we've put on the ground, and that is going to be the area that we're going to calculate the comfort over. The area that we calculate does not have to be flat, and it doesn't have to be on the ground at zero like this. It can be mezzanine levels, walkways, anything like that. They can be multiple patches, and they can be overlapping and in 3D space. It can even be mountainous terrain or anything like that. So in this case, it's just a very simple flat domain. So just going into the details of how we set up the virtual wind tunnel, it's just the same as before. We've got our B-reps that represent our buildings. The only difference is now that we have this rectangular ground plane, we've actually separated that out and we've assigned it a special name, and we've called it ground plane. The reason why we've done that is because we want to keep track of the name of this throughout the calculation. These other buildings can be just given a random name or a UUID, but we want to keep track of that ground plane also so that we can visualize it later in ParaView. We set up the domain just as we did in the previous tutorial, which sets the box around it. We get the names from these B-reps and we create a primitive mesh object, and we set those names that we got from the B-reps to the primitive mesh. So now we have a bunch of primitive mesh objects that have the same names as we've assigned to these B-reps. Similarly, we set mesh levels, so the building surfaces will have a mesh level of 3 and the ground plane is going to have a mesh level of 2. We can set refinement region if you would like, and also boundary layer meshes and other advanced meshes. I haven't actually done it in this case, but I've put an example here of what a refinement region might look like and how you might do that. The boundary conditions are all the same as what we used in the virtual wind tunnel. From there on, it's pretty straightforward. We're going to use Simple Foam Solver. We're going to run block mesh into Savvy Hex Mesh. We're going to then calculate, using the virtual wind tunnel, 8 wind angles at 45-degree increments. And when you've done that, the results will come out looking like this. And here's the virtual wind tunnel folder, and we're going to have all the wind angles at 45-degree increments here. Keep in mind, it doesn't have to be 45-degree increments that you do. You can do as many or as few as you want. So now that we're done with the virtual wind tunnel calculation, we want to run the actual urban comfort calculations and calculate the thresholds. This is done using the wind threshold component, and all that's required from this is the directory where the virtual wind tunnel folder results are kept. So you don't actually have to even run a virtual wind tunnel beforehand. If you have pre-existing cached virtual wind tunnel results from another project or whatever it might be in the same format as comes out of the virtual wind tunnel, you can just feed that directory name into this component. You need an Energy Plus weather file. In this case, we're using Perth, Western Australia, and it's being kept in C drive ODS here. So you just have to make sure you have a weather file, and that's the reason why it's highlighted in red. We're going to do the calculation over the ground plane, but again, this could be a list of multiple patches. It doesn't have to just be one, it could be many patches, and you don't have to put them in here manually necessarily. You could actually use the get names component and get the names from way back here and feed them into the wind threshold component. The reference velocity in this case is 5 meters per second, which is what we've used here as our inlet velocity for the virtual wind tunnel. The thresholds here are basically taken from the Lawson's criteria, corresponding to Beaufort 4 and Beaufort 3, I believe. I've labeled these walk-through at 8 meters per second and sitting at 5.5. However, I could have called this BF4 and BF3, for example, for Beaufort Strength 4 and Beaufort Strength 3. The way that these thresholds work is that for each time that is calculated, the wind threshold for that particular velocity is calculated, and it is assigned to a field that has a label walk through or BF4 or whatever it might be. So the name is not so important. It just creates a field, in this case called sitting and walk through, which give the percentage of time that cells across the ground plane at 1.2 meters above it, exceeding that particular velocity. And you'll see what that looks like later in ParaView. And the Z offset is the height above the ground plane at which we want to actually get the wind velocities. So in this case, the Z offset is 1.2 meters, which is about chest high. The time date ranges here are the times of the year that you would like to calculate. So what this wind threshold component is going to do is it is going to take the virtual wind tunnel folder here and the virtual wind tunnel results, and it's going to process those and create a new OpenFOAM output directory called Urban Comfort. And inside of this is going to be all these time-stamped results, just like a normal OpenFOAM folder has. However, the times of these results, time 1, 2, 3, and so on, will correspond to the results for these particular times of the year. So that's all that's required to really run the wind threshold calculations. I'll just explain briefly what's happening down here. This is mostly for the benefit of the tutorial, so that you can press a single button on the left-hand side and the calculation will run through. But basically what's happening here is that all of the long-running queues in Swift are designed to run asynchronously and non-blocking on the interface. So that means that they will run in the background and you can still keep using the Grasshopper interface while a calculation is running in the background. The way that this works is that long-running processes and long-running calculations are set up to run on queues, and these queues are named. The default queue for the CFD, for running CFD cases, is called CFD run. And all that we're doing here is we're telling this wind threshold component that we would like the calculations to run on a different queue, and we're going to call the queue wind threshold, and we're going to set the maximum number of concurrent threads to 4, which will mean that we can have 4 of these times of year being calculated at any particular time. The reason why I've set it to 4 is because I'm on a quad-core computer. If you had more CPUs, you could set that to a higher number and you would make maximum use of your CPUs. What's happening here is we are creating the queue, but we are then blocking it. We're telling it that it should not run anything from the wind threshold queue until the CFD run queue is finished. However, it is important to point out here that you don't need this wait for queue block. You can simply remove this block and replace it with a button, in which case you would just manually wait until the virtual wind tunnel is complete, and then once the virtual wind tunnel is definitely completed, you press a button that would start running the wind threshold calculations. You would still need this set queue though to create the queue upon which the calculation will run. So that's it. That's all you need to do to set up the Urban Comfort calculation. Now in the tutorial, if you go back and press the button here, it will run through, do the complete virtual wind tunnel calculation, and then when they are complete, it will run the wind threshold calculations. What you end up with is a folder called Urban Comfort, in the same directory as a virtual wind tunnel folder, that has all of the results laid out. You can open up ParaView and load up the case.foam file to open up that case. When you're loading in the patches, you only need the ground plane because that's the only plane that we calculated. So you can bring in the others, but they'll just show you 0 or null results. So the ground plane is the only plane where something interesting is going to happen. You can visualize the U average. This is the average velocity field, and immediately you can see you've got all the times of year. However, what we want to do is take these threshold calculations. If you look at sitting here, you'll see that we've got percentage values here from 0 up to 48%, and this is the percentage of time that the wind is exceeding 5.5 meters per second for this particular time of year. And you can see that changes for all the different times of year depending upon the prevailing wind conditions and so on and so on. We've got the same for walkthrough, which was for 8 meters per second. So this is showing the percentage of times that the wind is exceeding 8 meters per second throughout the ground plane. And you can see this happens less frequently. This is on a scale from 0 to 24%. So now what we want to do is turn these sitting and walk-through thresholds, which I really should have called Beaufort 3, Beaufort 4, but mostly 8 meters per second corresponds to walk-through and 5.5 corresponds to sitting and standing, so that's why I use those labels. but we want to turn these threshold values into a comfort map. So the way that we're going to do that is we use the calculator tool. And what we want to first of all do is create, let's call a field called over. And this is going to be the time that we're exceeding the criteria, the acceptability criteria for walking, which I believe is if walk through, so Beaufort 4 is greater than 0.04, so greater than 4%. So we'll do that, and that's going to give us this sort of a map. We'll then apply another calculator, and we'll call it walk, because this is going to give the regions that are greater than the criteria for standing. So you'll see how we're going to aggregate these results later. So what we do here is we're going to take the sitting result, and it's going to be greater than 0.06, so greater than 6%. That means we're exceeding the standing criteria, and we're in the walking criteria by that point. So we do that, and that gives that result. Fine. So then we want to add another calculator, and we'll call this one standing, because this is going to be the when the sitting is greater than 0.01, so greater than 1%, and this is when you're exceeding the criteria for sitting and seated activities, but and you're in the realm of standing, let's say. So that will look like this, and then we're going to finally add the sit criteria, and that's basically going to be anything else, any other region. So we'll take sitting greater than -1 in this case, because basically what we just want to do is have everywhere else that we haven't covered in those previous layers, let's say. So that's that. And finally, the final calculator we're now going to do is we'll call it comfort, and it's going to be the summation of those layers that we created previously. They're graduating layers, and it was sit plus stand plus walk plus over. And when you do that, you've created this layered, and you can see we're on a scale from 1 to 4. 1 would be the minimum area where we were just meeting that minimum criteria, basically anything that wasn't anything else. And number 2 would be where you're starting to get into the standing realm. Number 3 is when you're exceeding standing, but you're into the realm of walking. And number 4 is when you're up over those criteria. You could add more layers and more percentages and other criteria, so you can fiddle the numbers around. You could do anything you want with this, but this idea of layering up the results in gradually worse and worse levels will give you maps like this. You can then obviously, once you've got that, you can color them any way you like this. So that's how you get the comfort maps. Obviously, you can still bring in the geometry, add that in. However, it shows you the results on the ground plane at the moment. But remember, we calculated this comfort map at 1.2 meters above the ground plane. The reason why that is because even though the velocities are sampled at 1.2 meters above, we still mapped the results back onto the ground plane patch. So when you visualize it in 3D, you will end up with it overlapping. You can fix it up quite easily by just going up to your final comfort filter that you've applied there and applying a filter transform and translate that up 1.2 in the Z direction. And there you go. Now there's your comfort map at 1.2 meters above. You might also want to color the buildings white. So that's how you develop a comfort map in Swift and visualize the results in ParaView. Please support this project. You can contact us directly or go to Patreon to look at our individual or corporate supporter packages with associated rewards.